All right, in today's lab work, we're going to be examining friction. Why is the second law of motion important in our friction lab? We're going to have four forces acting on our physics block. We have its weight acting down. We're going to vary the mass and therefore the weight today. The normal force will always be equal to that, provided we don't sort of break the table. We don't put so much mass on it that the table just sort of crashes underneath. So as long as the table stays secure, the normal force we know is equal to gravity because there's no acceleration in that direction. So no acceleration means the forces must be equal to each other. Likewise, in the x direction, the applied force will be equal to, I'm sorry, I should have pointed down here for that a moment ago. Like the weight equals the normal force, and likewise, the applied force equals the friction, because these two forces are going to be balanced as long as we pull along a constant velocity. All right, so let's go ahead and start collecting some data. You can see that we've got our first data point there for you. And I think what I'll do now is I got enough data we like. We can kind of I'll go back and forth between the chalkboard here and the lab bench here. And we'll fill that in. Okay, there we go. So being an in-person student, when you're like looking up at the chalkboard for a bit, you see that, and looking back down at your paper, looking at the lab apparatus. Here we go. Now, the surfaces we're testing are wood and wood. Okay, so two wooden surfaces. And I guess there's some kind of a finish on this. I'm not really sure what it is. This even seems like it's been sort of. So this is 0.25. This is 1 kilo. We got our 1.25 kilos. I don't think we really need this string here. The string's mass is negligible. Oh, an important thing about the spring scale, we wouldn't want to introduce a zero error. Okay, so let me see if I can find a good view where the light doesn't sort of. So right now there's 0 newtons of force acting on it, right? There's no force sort of pulling down on it. And so you just want to make sure that like where we're reading it, sort of like the top of this syringe thing, is on 0. And then you can calibrate it with this sort of screw at the top, and so that would move it up and down. So if you first, get this out of the, if you says, all right, here's spring scales, everybody sort of grab one, you look at it, it's way above 0. Again, I wish I could sort of show you that, like the glare from the light bulb. There's 0. There. So see how that's above 0? So you want to adjust it. That's called a zero error, and that's a systematic error. That's an error that we can eliminate by just being careful and say, oh, my instrument should be calibrated so that when there is no independent variable, it's not showing anything. All right, so now the dependent variable, how much friction is there? So I pull this along, and it's not quite at 5. Remember, I have to disturb it to accelerate it, but then once I do, I can just let it kind of, go along at constant velocity. So I'm not accelerating it anymore. And it's just under 5 newtons. I can't be much more accurate than like that. That, sort of calibrated to the newton. You can maybe use your judgment and say, oh, like it's in between 4 and 5. I'm going to call it 4.5. And that's up to you as the experimentalist doing it. That, okay, I feel like I can use my judgment to say it's neither 4 nor 5, even though those are the lines on my apparatus. I'll call it 4.5. I feel good about just saying it's 4. So if there's 4 newtons of applied force, that's literally what I'm measuring, right? Like how much strength it took me to pull it, how much force at a pull, but I was really measuring the friction, right? Because we're sort of thinking how important this Newton's second law is. Okay, because we pulled it with constant velocity, that means acceleration is 0, which means these forces must have been equal. So 4 newtons. As a quick calculation, we can say 4 divided by 12, that's about a third, right? So you might expect the coefficient of friction between wood and wood to be about a third, you know, 0.3 repeating. More precisely, we say 4 divided by 12.26. And you can see why I would do that. If I want to know mu, it's just the ratio of the friction to the normal force, right? Dividing side by the normal force. So this number divided by this number gives you an idea about what you would expect, 0.326, you know, but that's a very weak conclusion, okay? To take a single data point and go, okay, it gives you an idea, all right? But what we need to do now is vary the mass and therefore the weight, see how this changes. Does it depend on that? The dependent variable, sort of the idea in science is because I changed this, that's why I notice a difference over here. When you change something and you notice a difference in the dependent variable, you're like, oh, it's because I changed it. That's why it's different. There's some law of nature going on here. That's right at the heart of science. All right, so we'll go back down here. The most exciting part of lab day is we vary the independent variable. Yeah. All right. A lot of excitement for that. 2.25 kilograms now. Everybody with the calculator knows that 2.25 kilograms of mass here on planet Earth has a weight of 2.25 kilograms of mass has a weight of, come on, you learners, waiting on you.
22.07 newtons.
Thank you. 22.07 newtons of weight means 22.07 newtons of normal force. As it sits on the table, sorry, everybody. As it sits on the table, it's acting, there's 22.07 newtons of force acting down, and the table, the wooden block, the wooden plank, exerts 22.07 newtons of force back up. There you go. Now let's pull it along. So now it's just beyond the 5 Newton mark, but not at 10, somewhere in between there. It looks like 6 or 7. A little zoomed in view. Where the low row should go, you guys. The other day, something got the high 5 up there. There, now you can clearly see it for yourself, right? Either 6 or 7. And indeed, how sort of the surface itself isn't uniform, right? There's sort of, like we mentioned yesterday, different sort of bumps and divots and things like that that are sort of the source of the friction. And so it does sort of vary a little bit, but it's right around 6 or 7. 7 newtons. 7 newtons of force by my best judgment. So testing a relationship with k values would be where we'd sort of take two data points like this. And we'd have sort of an equation, what theory suggests. And we'd say, well, if this is a constant, how constant is it? In other words, there's some uncertainties in the way that we collect this data. So we can't really know the true value. We can say, well, we measure it to be 7, but plus or minus maybe 1 Newton, because that's how precise my scale is. And so because there's uncertainties in each of these measurements, there's even uncertainty in how we measure the weight, right? So there's uncertainty in that also. So there's uncertainty in each one of these. So you might expect then that the constant here might be off by a little bit, just due to the uncertainty. And so in physics, we have to have a rule that sort of says, well, is the constant close enough that it's basically constant? Even though our calculator might not show the exact same number. We're like, oh, 1.99, 2.01, that's close enough, it's basically 2. They're both basically 2. And the only reason they're a little bit different is because of the uncertainties in the method. And so you just sort of, before we would dedicate the resources to doing a full-blown experiment like this, where we're gonna like get 7 data points, right? I get 7. It's like, well, do we even know if there's anything to this idea? Let's just test 2 of them, see if we get roughly a constant. And if we do, then we can say, let's do a better experiment. And so the very first 2 marks you can earn on that paper 3, where you're doing the second experiment, testing a relationship with k values, is you'd say 2 data points is not enough. And if you look at the mark schemes for paper 3, year after year after year, that's always the very first suggestion for improvement. 2 data points are not enough to draw a valid conclusion. So what's the corresponding suggestion for improvement? Vary the quantity, collect more data, and plot a graph, which is what we're going to do. It's a stronger experiment. And so you do 2 experiments in paper 3. One is like this, where you actually collect data, you plot a graph, you find the slope, our favorite. The second one is like just testing 2 data points and then recognizing that that's a weaker form of an experiment. But maybe we're not prepared to sort of dedicate the full resources to doing a full-blown experiment. If there's nothing to this idea, if we're wrong about this, we don't want to do a whole experiment to kind of show that. We can just check it real quick with 2 data points and go, now the results do not support this relationship, therefore it's probably not true. Let's examine some other laws of the universe. Okay. All right. I can feel the anticipation in the room building for varying the independent variable. All right, a lot of excitement for that. Now we've got 3.25 kilograms. We'll fill in all that in a moment. 3.25 kilograms of mass has a certain weight, which we'll calculate in a moment. But when I pull 3.25 kilograms across the lab bench or across the wooden plank, I'm getting right at 10 newtons. Now, for the data table up here, I really didn't need to write those newtons here, right? Like I'm taking care of the units up here, so I already wrote them. I'm going to bother erasing, but that's superfluous. All right, what is 3.25 kilograms weigh here on Earth? Because wherever it is, it's 3.25 kilograms. We can move that mass to the moon, and it would still be 3.25 kilograms of mass. It's still made of that many atoms. But the pull of gravity on those atoms will be weaker on the moon, right? So it won't be somebody in person now. You get a chance for all the glory. 0.88. All right. And for everybody following along on YouTube, that's like, wait a minute, how are they doing this? How are they getting this number from this number? Remember, the force due to gravity is weight, mg, and g is where g equals, we're using 9.81 in this course, right? So we're just taking this number times 9.81, right? To get these. That's the weight in newtons. And it's still about a third, right? 10 divided by 31, remember 4 divided by was about a third, 10 divided by 31 is about a third still. So it's like, yeah, we're noticing a trend here. As we increase the mass and therefore the weight, it's getting harder and harder to pull this thing across the lab. We're squeezing together those atoms that are kind of like the rubbing of atoms together. It's like the source of the friction. We're pushing them together more, which is kind of how we can understand why friction would increase as we increase the weight. All right, let's have everybody settle down, please. We're getting a little bit out of hand here on lab day. I know I'm just as excited as you. Okay, but we got to maintain some order. When you come to work and it's high, just will have the lab fall out of order like this. I'm not wearing face shields or nothing. All right, we got 4.25 kilos now. You know, last semester, students used to cheer when I varied the independent variable. They used to cheer. Check it on YouTube. I'm just saying, you guys. All right. You know, now that I reflect back on it, maybe they weren't genuinely excited about varying the independent variable. They're doing it just to like patronize you. Was that the case? All right, let's get back on track here. I'll just dwell on that for the rest of the lab day. Maybe it isn't as awesome as I thought. All right, we got 4.25 kilos. And it takes like 13 newtons of force to pull that across. All right. You learners can hear also. I think the mic picks up you guys better, so when I close this, it's like, you can hear. All right, 4.25 kilos. Let's go ahead and make sure we're filling in our data table. You learners last time, in-person students. Oh, I guess 2 times ago we had e-learners in person. My turn. 41.69. 41.69. We got 4 data points. And we want to go for 7. Okay. But I think I'm going to run out of room. You could draw a line between 2 points, you know. Okay. So you really, I mean, you could have 2 data points and say, well, here's my best fit line to the dot. But when you look at 7 data points, there might be a slightly different trend in that. So the more data, the better. You can kind of see the trend in that. So we want to try to get 7. Maybe I'll just try to squeeze more data points on there. All right. It's everybody's chance for redemption now. It's okay, even if you're just doing it to patronize you right now. This is all I got going for you guys on lab day. Varying the independent variable. Help me out here. Let's have some excitement for 5.25 kilos. Here we go. Vary the independent variable. Yes. Yeah. Everybody's excited about it. All right. Some people too cool for school. I get it. You know, but come on, cheering for that. That's not exciting. I'm keeping it real here. All right. At 5.25 kilograms of mass, a certain amount of weight, it's a good time to maybe talk about static friction versus kinetic friction. This is an object at rest, right? And to sort of get it moving, it has a tendency to resist change in motion. All this mass here is inertia, tendency to resist change in motion. So it does actually cost me more force to get it moving And then once it's moving, the force meter kind of drops down and shows me actually what we say the coefficient of kinetic friction. So there's actually sort of more sophisticated sort of theoretical interpretation. We could say, well, there's a coefficient of static friction. Like we could put a little subscript S here. If you're just looking at where does the force meter sort of jump up to just as I get it moving. We're really examining here the coefficient of kinetic friction. It's moving, right? We're moving it along at constant velocity. And so we know empirically by doing these experiments that the coefficient of static friction is always greater than the coefficient of kinetic friction. Once it's moving, this coefficient of friction is lower. It always, has a higher coefficient of static friction to get it sort of moving from rest, from, station to static. So just kind of be aware of that. Very, sort of more precisely, the plane that you're reporting is the coefficient of kinetic friction between wood and wood is, whatever we get will be the slope of the nested line once we plot it out. 5.25 kilograms, just to give you an idea like how massive that is. There is 2.2 pounds in a kilo, so like 5 1/4, it's like 15 pounds or something like that. It's about 15 pounds here. So it's at like over 20 right now. And it jumps to like 25 newtons when I pull it. But then as it moves, it's harder and harder to get like constant velocity because it doesn't. It sort of stops at all those places on the surface where it's like, oh, it's a little bit stickier here. It's sort of averaging over all of that when you just pull it across the entire plane. It's closer to 20 as it's moving, but it's above 25 for that static friction. That's actually close. No, it's between 15 and 20. And it seems to kind of vary between them depending on sort of like what part of this I'm sliding it over. About 20. All right, so the applied force was 20 for that one. How much force it cost once it was moving, which means there was 20 newtons of friction opposing it. Because it was 5.25 kilograms of mass, we take 5.25 times 9.81 to calculate the weight, the force due to gravity. So we want to call it out. Good. 51.50. And even though that 0 is like you don't really need to write it, you should record it to keep consistency in your data table. Right, like 2 digits everywhere. So 51.50 there. And then another data point. So maybe. All right, moment to vary the independent variable. Here we go, and 6.25. All right, yeah. Doesn't get much more exciting than that in the physics lab. Varying the independent variable. That's what we do on lab day. So I thought we measured the dependent variable. You're right. Do that. Both are important. All right, we got 6.25 kilos, and it's going to take 24 newtons to pull that off. So now we got 6.25 kilograms, 24. It's getting harder and harder to pull this. Okay. I'm having to exert ever greater force. 6.25 kilos times 9.81 newtons per kilo, right? Remember, meters per second squared, same thing as a newton per kilo. And so that is, remember, we haven't talked about that. I think we did actually when we looked at calculating local G, like we saw it theoretically. So this one is 61.31. 1, 2, 3, 4, 5, 6. So close. All right, for the 7th data point, I'm not going to write it up on my chalkboard. You're going to write it in your journal. Okay? So you probably have enough space in your journal to add another data point. If not, let's flip the page. Let's go to the same page. All right, we're going to get one more data point, but I'm not going to write it down. Thank you. Thank you for that. Sorry, everybody, you didn't get a chance to be as excited about that as everybody here in the lab. I forgot to train the camera on our apparatus. Don't worry, there'll be plenty of lab days to come. 7.25 kilograms. You write that down, right? Go ahead and calculate the weight right now. So I'll give you 9.81 seconds to do that. Did you come up with 71.12? If so, good job, you two. Well done. Everybody in class got it. The pull force for 7.25 newtons. Well, I'll just let you read it off here since you're doing this one. So everybody can clearly see what that is now. There you go. All right. So write that number down and you just were able to read. No problem. Okay, this is why we need like a camera here in the physics lab. You like zoom in and enhance this. So I will tell you that it really does jump around a lot. It's hard to get a reading. So as I begin to pull, it's like 35, and then once it starts moving, it's like, okay, I'm an object in motion. So it's a force of habit. There's the data table that you already have. So now you've got your 7.25, your 70 something, 71.12, 71.12, 30, 30. Okay, 30 newtons of force to move that. All right, you've got 7 data points. I've got 6. It's really important that you all are doing your graphs for your lab work. Okay, it's the first thing I look at when you turn in your work. All right, I'm trying to see the graph. I'm trying to see, did you scale the axes appropriately? Did you label the quantities and the units on each axis? Plot this data, but don't use the data points to do the slope calculation. Like you can say, because these are my x coordinates and these are my y coordinates, I could just do y2 minus or y2 minus y1 over x2 minus x1. But do not use these numbers in your calculations. I'm telling you, don't use them. Use them to plot where the data goes on your evenly scaled graph. So you just choose nice round numbers to go up by on the x and y axis. And that way, when you go to draw your best fit line, you're bound to find some points on that line that will intersect the gridding of your graph paper. And you'll be able to read off their coordinates. And the line, the best fit line that represents the trend in this data, is more accurate than any 2 of these data points. Drawing a trend line that represents the trend in 7 data points is more accurate than any 2 of them, which is what I'll tell you as a note if you use data points to calculate. What was the point of collecting 7 if you're only going to use 2? We will only need to collect 2 to do a calculation that way. So it will cost you marks. I mean, as a last resort, you can. If you scour the plot and you're like, I don't see any points that intersect the gridding of my graph paper. If you use the graph paper that we want to kind of get used to in ACE physics, it looks like this. Again, you can find this on paper 3, like just like where we go on. So see how tiny the squares are on this graph paper? You're bound to find points that intersect the gridding of your graph paper when you use it that small. And you're not required to use this in pre-A's. I think it's like, if you already know, I'm definitely taking ACE physics, I say use this graph paper. Just it's tough on the eyes. You're like, I'm used to my regular old graph paper. I got some of that back there too. In fact, I buy it by the box from Walmart. A lot of graph paper, you have a strong need for graph paper in my line of work. Okay. Don't judge me because I'm buying graph paper by the box. So I got some other graph paper back there. All right, there's your data. Does anybody have any questions about how to go about the analysis now? Plot these numbers on the y-axis. So your y-axis will be scaled from like 0 to 25, maybe go up by 5 or something. I'm actually going to take this data set back to my document camera, and I'm going to go ahead and plot it just as like a work example for everybody to just show you what I mean, because it is so important. Like if this was tough for the first couple of labs, don't just say, well, that's something I'm just going to not worry about this course. I'll just lose all the points for those labs. They're tough. Don't have that strategy. You need those points, okay? That's like the one thing you should take out of this course is, how to interpret the data that we collect in the lab, right? So this is lab-based. All right, so that's the data collection. We'll see you next time for the analysis.